webinar. My name is Sean Parkinson. I'm a senior software engineer at wolfSSL. Worked on the TLS 1.3 implementation, designed implementation. And today I'll be talking about TLS 1.3, what it is and why you should use it. I will first go into an introduction of TLS 1.3 and some of the new features, some of the features. Then I'll be talking about the advantages of TLS 1.3 over 1.2, the performance and security features that make it attractive. After that, I'll discuss the status of the draft standard. After many years of development, where is it at? Are we there yet? Finally, I'll tell you how to use TLS 1.3 with wolfSSL, discussing a few of the APIs for the new features as well. So TLS 1.3 is the newest version of the SSL TLS protocol. It's a standard, which is a standard for securing communications over TCP. The standard's been in development for over 4 years, or about 4 years, and a lot has changed from TLS 1.2. There have been many new ideas about how to improve the security and the performance of the protocol. And the result has been that there's a lot of changes to the formats of the messages. And some new ones have been added as well. So let's take a look at some of the features. So one of the most important changes has been with how TLS performs Presumption. In previous versions, you were using a session ID to identify to the server which session you want to resume. Now, this required the server to contain, or to hold state so that it knew what session information belonged with that session ID. There is an extension to TLS 1.2 that came out called session tickets. And using session tickets means that the server sends an encrypted version of the session information to the client after handshake. Now, the information can be sent back, the encrypted version information can be sent back to the server when the client wants to resume a session. Now, only the servers that hold the key to decrypt the session information can resume the session. And all the information is contained, ready for it to resume the handshake, and therefore no session information, that server state is required to be able to do this. There has been some vulnerabilities that have been found in TLS, and they've revolved around the session resumption or renegotiation feature. So with TLS 1.3, they decided to scrap that and just to go with what they know is secure, the session tickets. You can also use pre-shared keys to do a resumption style handshake, and it's just as quick. Another change that has been made with respect to resumption is that by default, doing DH or ECDH is required. So you're creating a shared secret for in the handshake, and that's used to create the keys for the handshake. So that means that you have forward secrecy. This is a cost, but overall, for the overall security, this is important. There's been a new and controversial feature that's been added to TLS 1.3, and that's called zero round trip time handshake with early data. This handshake has the client sending application data protected by a key derived from a previous session. And this is including the client hello. This means you can get small amounts of data from the client immediately rather than waiting for the handshake to complete. There are security issues with this feature though. And this is why there's been much argument on the working group about whether it should be included or not. As the same key and IV are used each time, there is no forward secrecy. And there is the risk of a replay attack. If the same key is being used to encrypt the data, then replaying the same early data will mean that it will decrypt fine. So you need to be careful about this. Another new feature is post-handshake authentication. This is referring to the client authentication using certificates. If a client is connecting to a website where some of the pages need authentication and others don't, the server may delay client auth until after it has seen the URI request. That is, the client auth happens post-handshake. Also, for long-term connections like VPNs, the keys and IVs can be updated post-handshake using new handshake messages. This is not a feature that is expected to be commonly used, but a connection that has been open for a day or has had hundreds of megabytes sent across should be rekeyed. This is done by requesting a key and IV update through a message, handshake message. So now let's talk about the advantages of TLS 1.3 over 1.2. There are two major reasons, two major advantages. 1.3 is more secure, and it has fewer round trips in the handshake, which means which is faster in negotiation. So let's start with security. Only secure ciphers have been included in the standard. This is actually a little misleading, and I'll get back to that later in the slides. In essence, when performing a full handshake, you must perform a Diffie-Hellman style key exchange. This ensures perfect forward secrecy. That is, each handshake is protected by a unique secret based on the key exchange secret rather than known only to the client server. Many groups were not happy about this as it makes monitoring of networks harder. Many email chains went around about this in the working group mailing list, and it was finally agreed that the standard must not be weakened for interception. The dangers of abuse or accidentally reducing security are too great. Another security improvement has been to encrypt all handshake messages after the server hello. The key and IV used for encryption are based on the key exchange secret and are therefore secure. Next is the resumption. And as I've explained before, it's been changed to use the more secure session tickets. And PFS is available with session tickets and PSK as well. The key derivation algorithms also been updated. Previously, the key derivation function was designed by those writing SSL and TLS and didn't have a security proof. TLS 1.3 uses a standardized function that is both an RFC and a NIST standard. So there's greater confidence in the security of the keys derivation algorithm. And finally, RSA PSS is being used for signatures in the handshake. In the past, RSA PKCS 1.5 signatures have been used, and they're still in use with certificates for the foreseeable future. Hopefully, RSA PSS will become standard for certificates, but until then, we'll be using PKCS 1.5. RSA PSS has a security proof and is more secure against attacks due to its probability signature scheme, which means that there's random data being inserted into the signature algorithm and makes it harder to put in malicious data or to try to use a random oracle. So let's look at the performance. So there are fewer round trips in the handshake. In detail, the key exchange is performed in one round trip in TLS 1.3. The first round. The client hello contains the client's public key. The server creates its key pair and secret and sends back its public key. In fact, the server now sends all the information to complete the handshake and can even send application data, all in the server's first flight. So the client then calculates the secret and finishes the handshake, sending back application data. Now let's compare this to TLS 1.2. The client hello is sent, the server creates a key pair and sends the server's public key. The client creates a key pair and calculates the secret, returns its public key. This is a whole half round trip slower. The application data is now sent in the next server's flight, the second server flight. There's a whole round trip behind TLS 1.3. This is a performance gain for TLS 1.3 and especially in high performance, high latency networks. Having to wait that extra round trip could mean hundreds of milliseconds. The faster handshake is the 0 RTT. So what does this mean? The data is sent, the early data is sent with the client hello as a separate application layer message and encrypted with a key derived from the last session. To be able to get a small amount of data immediately is great for embedded systems like sensors, say. Okay, so where is the draft specification in the IETF? The draft has seen much debate in person and on the mailing lists over the last 4 years. The working group has submitted the draft for review by the IESG and has finally been approved as of the beginning of April. There will be no more changes. The standard is finished. It's in the hands of an editor to tidy it up and will hopefully be released as an RFC, as is, in a couple of months. I've heard from other people involved with TLS 1.3 that it may be 3 to 4 months before the this RFC will come out. So because of that, I looked back at TLS 1.2 to see how long it took once the editor had finished before it was released as an RFC. And it turns out that was about 4 months. So I guess that's where he got the idea from. Hopefully it won't take that long this time. I'm not familiar with that back end of the process, but my hope is that it'll be 2 to 3 months. So the last draft version is 28, and that came out on March 20, and there will be no more changes. There hasn't been any wire format changes since draft 25 back in mid-February. And the latest changes have been clarifications and spelling grammar fixes since then. So now I'll tell you about using TLS 1.3 in wolfSSL. So there's been many drafts that have come out in the last year, and wolfSSL supports a number of these. The first draft that came out was draft 18, and it was an early version that had been supported by browsers and web servers to see how things were going. They were mainly testing implementation, interoperability, and any network issues that may arise. As a result of these tests, and they're quite extensive tests, and lots of measurements were going on to see how it was performing, draft 22 and 23 came out with changes to support middle boxes. Now, middle boxes, I'm talking about those devices that sit between any client and server that either intercept it or just there to read it and to monitor it. For example, in a corporate network, there are likely to be boxes or devices that are monitoring the network for security reasons. If they see a TLS packet that they don't like or understand, say if it's an unusual looking TLS 1.3 packet, then they may choose to just discard it or not let it through, basically. Over time, these middle boxes will be replaced or updated, but the specification needs to work today, and they had to update it to work in spite of them. So there's a few things in there that in the draft 22 and 23 that were added that made it possible that it will work in more network architectures. Draft 25 introduced a change to the way that the encryption is performed. Previously, the authentication code was calculated just on the data encrypted. The handshake message or application data was encrypted and authenticated. But draft 25 changed this. Now the record header is also part of the authentication code calculation. It was unclear as why they included this. They didn't spell it out exactly on the mailing list, but I can see that it's important for security reasons that you include everything that's being sent in the packet as included in the authentication data. this makes the draft 25 become incompatible with previous versions. So if you're using anything from 25 to 28, then it will not work with any of the other previous versions. The code list will not, well, any encrypted data won't be able to be decrypted by the other end. It'll come up with a authentication data error. So even though you can compile wolfSSL to older drafts, and we will be taking those drafts away as time goes by, you should be using the latest draft 28 changes. They've gone into the master branch just recently, and they will be part of the next wolfSSL release. So how do you use TLS 1.3 and wolfSSL with the APIs? So what do you need to change about your code? Well, nothing. In the simplest case, if you're using wolfSSL v23 client method or server method, then it will negotiate the highest supported protocol. If that's TLS 1.3 on both sides, it'll do 1.3, or it'll downgrade to TLS 1.2 or whatever is supported. You just need to compile up the code to include TLS 1.3 using the configuration option -- enable TLS 1.3, and you'll be able to do it. Also, if you just want to do TLS 1.3, there's new APIs for that. There's TLS v13 client method and server method, and these will only do 1.3. There's no downgrading available. So new software suites have changed a bit, as I talked about earlier. Previously in 1.2, the software suite included the key exchange and authentication algorithm. This is no longer the case, as the client's key, the key pair is sent in the client hello, and thus the negotiation of key exchange algorithm happens separately. And while they're at it, they pulled out the authentication algorithm as well, with PSK being negotiated in the client hello as well. So it just made it more flexible, that you didn't have to have 20,000 different cipher suites that only varied upon the key exchange and authentication algorithm. So there's only 5 strings now that you need to worry about. 2 are using AES GCM at different strengths, and one is the CHA 20.1305, and it's been basically added as a backup to AES GCM if there's attack found on it. Though, from an implementation point of view, it can be faster on processes that don't have hardware support, like built-in instructions doing AES and GCM. Also, AES CCM was included. There are some standards out there that have been for embedded systems that are quite popular, that they decided that they needed to be able to support in the future as well. So these are the strings that you need to pass in when setting the software suites for TLS 1.3, and the TLS 1.2 ones can be included at the same time and will work alongside them. If the client and server can't match on a TLS 1.3 cipher suite and TLS 1.2 is available, it will downgrade to the TLS 1.2 cipher suites that are listed, that are being negotiated. Okay, so one major change is that if you support Presumption, then you'll need to implement a callback that encrypts and decrypts session tickets in the application. To set the callback, you need to use wolfSSL context set ticket inc callback. So you need to implement how you store the key, the encryption key, and if there's multiple servers, then how you can share that between the servers. There's a good example of how to do this in example server.c and SSL test.h. This example uses CHA poly 1305, but you can use anything. Any encryption algorithm that's available to you on on the device. Next is early data. As early data has different security profile as compared to normal application data, as I said, it's not protected against replay attacks. Special APIs are provided to read and write it. So only the client can write data, and client applications must use wolfSSL write early data to get the early data to be sent. Servers must use read early data to receive the data, and it will not be seen, the early data will not be seen if you just do a wolfSSL read. But if the client doesn't send any early data, then that's okay. The wolfSSL read early data will still do the connection, and will just return that there's no early data seen. And you can continue the handshake as normal. To limit the risk of using early data, you can set the maximum amount of early data in the establishing session using wolfSSL set max early data. So this value is included in the session ticket from the server to the client. And when the server receives it back, it will know how much data it's willing to read. Any data after that will be ignored. The client is also advised in the session ticket handshake message as to how much early data will be allowed. So what other APIs need to be aware of? So using Diffie-Hellman with pre-shared keys is a default behavior, but this can be turned off on the client. Using wolfSSL context no DHE PSK, so PSK is usually termed to include session tickets as well as actual pre-shared keys. You can disable that particular using Diffie-Hellman key exchange for a session, resumption session, or for PSK handshakes. Post-handshake authentication is allowed on the client side with wolfSSL context allow post-handshake auth, funnily enough, and is requested after the handshake with wolfSSL request certificate. So the client says wolfSSL allow the post-handshake auth to occur. I will allow you to send my certificate after the handshake. And the server says is requested to request the certificate with the wolfSSL request certificate call, and a handshake message is sent at that time. And if the client has allowed it, it will respond with a certificate and a responsible, and the return will come back from the wolfSSL request certificate function. Key share is the extension sent in a client hello and returned in the server hello containing the public key for a key exchange. So if you want to use a hello retry request to negotiate which key exchange algorithm to use, then call wolfSSL no key shares. As I said, the client hello contains the key pairs from the client. But if you don't actually know which algorithms the server supports, then you can send an empty key share extension, and it will require the server to reply with a hello retry request to say, send the client hello again. I can't send my server hello yet. Try again with these parameters, these security parameters that I've specified. So that's helpful if you are dealing with new servers where you don't know what's going on. But hopefully, if you control both ends, or you have some previous idea of what's going on with them, with the server, then you can specify exactly which key share you want to use, which key share algorithm you can use. You can do that with wolfSSL use key share API. So with that, you specify the key share algorithm, and you can make multiple calls so that you can send multiple key shares. Say, if you speculatively want to send a Diffie-Hellman key share and a ECC one with P2T6, then you can make two calls and it will generate both key pairs and include them in the client hello. By default, the wolfSSL will send key shares for the algorithms that have been compiled in. So to save some time, it's best to specify the key share algorithms that you prefer. There's also an API called wolfSSL send HR cookie, which on the server side includes a cookie which contains information about the previous client hello, so that it can be detected that this is a replay of the client hello in response to a hello retry request. So this is an extra security measure that's been added, and it's available through this wolfSend HR cookie. You can also update the keys and IVs during the post handshake at any time with the call to wolfSSL update keys. So this will cause a message to be sent and queued up in the application data, and it will ensure that the keys and IVs have been updated. The new messages after the new application data sent after the call will use the new keys and IVs. So that's it for the slides. Are there any questions?
Thanks, Sean. Yeah, there's a couple questions in the Q&A. And if anybody would like to ask a question, raise your hand and I will unmute you.
Okay, I'll just find the
Here,
Q&A.
I'll help you. Since all handshake messages after server hello are encrypted, is this why I can't see the server certificate in Wireshark capture when TLS 1.3 is in use?
Yes, that's correct. Yes. It's a good thing and a bad thing. It makes it harder to debug what's actually going on with the handshake and where there's problems, but we do want to make sure that the maximum protection is included. So anything after the server hello, the certificates, the finish message, anything like that, it's all encrypted, and you'll have to get the key pair post handshake, the secret, out of the server or client, and then you can process the handshake and see it in Wireshark. Wireshark has stated that it supports a number of versions of the TLS 1.3 protocol, including 18, 22, and 23, I believe.
Okay, great. The next question, what is the typical time for the single round trip to establish the session key?
Okay. That depends on the network latency. So I was doing some testing on my own computer with a client running on my computer and the server running on the same computer. So that meant that there was very low latency, and I was using optimized code. So I mean, it's fast. I was seeing like 0.16 something milliseconds to do a handshake. That sort of doesn't really mean anything. But if we compare that to the TLS 1.2, it's slower. It is actually slightly slower, and that's because there's, sorry, well, that's if you're doing resumption. It is slightly slower, and that's because there's a lot more hashing going on. To do the full handshake to establish the session key, then it is faster. Just basically the round trip. So yeah, there is differences because of the ordering of the handshake messages. Sometimes some work can be done on the client while it's waiting for the next message to come through. And that meant that in some cases it was faster, in some cases it was slower, but typically it's about the same.
Okay, will Wolf support several server sessions, say 16?
Having session tickets is up to it's up to the servers, I guess, to handle that. I mean, let me think about that a little more. Because it's stateless, then if you give out a server session, a session ticket, then it will just work. So I'm not exactly sure about any need to say have a cache anymore to do this. If you want to, you can keep a cache of the session tickets that are being handed out, so you know that if you see it again and it's been a while, then it will no longer be time. You can time it out and no longer be used. But there's information within the session ticket to say when it was handed out, and you don't need to do that on the server side. Next question.
Okay, when do you expect to release the final draft of TLS version 1.3?
In terms of wolfSSL, I'm not across the release schedule of the next, release schedule of wolfSSL. I'm sorry about that. It should be, and don't hold me to this, it should be in the next month. We should have a release from wolfSSL containing the final draft. There is an option to turn on the to change the version number, so it will always be able to going forward. When the final RFC comes out and people start using the new version in the packets, then you can just compile that in. The final draft of TLS v3 in terms of the specification, it's there. It just needs to wait a couple of months before the RFC is officially out.
Okay, thank you. Please describe in detail about key 4 updating. Which side generates the new key when, controlled by application of configuration?
Okay, so yeah, this is a bit of a funny one. If a client requests key IV updating, it requests it for one side. It may be able to request for the second side, the other side as well. And I can't remember off the top of my head. I should have looked at that more carefully, I guess, before I came to this presentation. So you can definitely say on your side only, you want to update the keys and IVs. So that means that the client will generate its new key and IV at that time, and all messages will include that. We'll be using that new key and IV on the right side. Now, the server is probably going to see that and say, okay, fine, they want to update keys. I should update keys too. So I'll respond to say that I'm using the new key and IV on my read side as a server, and I want you to change to the new key and IV, generate the new key and IV based upon the previous ones, and it'll send back, and it will start using those new keys and IVs for its application data going forward. So when the client sees this message, it will then know to update its keys and IVs, and it responds. Yeah, so there's a bit of a to and fro in there, but it's that's how it's done. It's either end can kick it off, and it can be just for one side at a time.
Thank you. Okay, next question. How do you derive the shared key in TLS 1.3?
So the shared key, I'm not sure which shared key is being referred to there.
Could you clarify the attendee who asked the question? It's a session key.
Okay, so the session key is derived using, I can't tell you off the top of my head what the standards are, but based upon the previous handshake keys. So it's based upon the ECDPM, the DPM key exchange key, and the handshake messages, all of them up to that point. And it's derived with some special text to make it uniquely identified using the new key derivation algorithm. So it's completely tying the new session back to the old session.
Okay, that is all the questions in the Q&A and chat. Does anybody else have any other questions? Well, that wraps up the presentation. Thank you.